And then let's make sure that everyone can see. All right. Can people see the screen clearly? All right. Good. Okay, fantastic. Also, please, since I'm on Zoom, feel free to call out questions. I'm not necessarily going to be looking up all the time, so I won't be able to see if your hand's raised. All right, so I've decided to lecture on a little bit of a different topic than I'm known for lecturing on in various schools, and it's something that I've developed an interest in the last couple of years. And I'd like to tell you a story that I think is very, very powerful for something that you may well have heard of in different ways, which is the concept of quantum sensing. In particular, I'll try to focus on a viewpoint that I think is a relatively universal way to think about sensing, which is through the lens of symmetry breaking. But we probably won't get to that lens until the sort of second or third lecture. In the beginning, I'll really try to teach you a little bit of just the framework of estimation theory, and how to think about sensing in general and parameter estimation. There's a couple of references here which I've been using and I found very, very helpful as I've learned about quantum sensing. I presume I'm happy to make the lecture notes available for you guys afterwards, so you don't need to be frantically copying down the references if it's difficult. I'm also not known for being the world's best handwriter, so if things are unclear, just really call out, even for clarification. I'm happy to answer. Good. So for any, I think, discussion or any lecture, especially in a school on quantum whatever, I think the first question one should always begin with is to ask the question, let us begin at asking the question, why quantum? And it's pretty common these days. I mean, we hear the word quantum in front of lots of things, computing, networking, simulation, sensing. And you guys are all here, so you've drank the Kool-Aid. But I think it's always a useful thing to ask ourselves why exactly quantum and what exactly we mean when we talk about something a la quantum sensing. So I'd like to offer, and there are more reasons than this, but I'd like to offer three reasons to start our journey off. The first reason why you might want to think about quantum sensing is that is because the thing you're trying to measure, you're measuring, is small. And that's just a very pragmatic thing. So in order to sense it, you need kind of good spatial resolution. And as you get down to nanoscale spatial resolution, inevitably the laws of quantum mechanics enter, whether you want it or not, and you end up having a sensor that behaves under the rules of quantum mechanics, whether you want to or not. A second reason might be because the thing you're trying to measure is quantum, because the thing is quantum. My favorite example of these types of things are certain fundamental quantities. For example, maybe the most classic one is the fine structure constant. So quantities, maybe the example is alpha. And in this case, it's again kind of obvious. Alpha is kind of first defined for many of you in the context of quantum electrodynamics or a G-2 experiment. If you want to measure something very, very precisely that is ultimately related to the laws of quantum mechanics, in order to make such a measurement, you probably need to get into the regime where the measurement details are again governed by the rules of quantum mechanics. And the last one is perhaps because some facets of quantum mechanics, in particular because entanglement can enhance, because entanglement can enhance the precision or the sensitivity of a measurement. And oftentimes in this case, we say the words that you'll hear me mention, and I'll be very specific about what I mean by that, is, for example, people try to oftentimes make measurements at the so-called Heisenberg limit. Okay? So these are three quite different reasons for why you might think about quantum sensing or sensing in the realm of quantum mechanics. And I would say that the first two perhaps ought to be grouped together in some sense, where you kind of naturally have to use sensors that are governed either because you really care about the spatial resolution or because the phenomenon you're interested in is very much intrinsically quantum mechanical, you might have to use sensors that are governed by quantum mechanics. And the last one, sort of, I would think of as a little bit of a different category, which is where you're trying to somehow harness quantum mechanics in order to make better measurements, better measurements than can be done in a classical world. I should say that in some way, the third is the most, is the most alluring at some level. But really, I think of the first two as just as good. So, depending on who you talk to, purists in the field might say that, well, quantum sensing really only refers to the third, or one should make a very, very careful distinction between, quantum enhanced sensors and quantum sensors where the sensing is just quantum mechanical because the rules are that way. I'm not such a purist. I think it's completely fine to think about the first two as quantum sensing as well. But I do understand that there's something a little bit more alluring about the fact that entanglement might, in principle, maybe you guys know, we wouldn't be lecturing about this otherwise, might in principle be able to allow us to make measurements that are more sensitive than would be allowed purely classically. Despite the fact that maybe the third motivation is a little bit more alluring, it should also be emphasized that in some sense, examples of the first two abound, but examples of the last one are kind of few and far between in the sense of really having situations where entanglement is absolutely essential for making a particular type of measurement or enhancing the sensitivity to be able to see a particularly small signal. One example, which I won't get into too much detail about, but which you may well know, is the measurements from LIGO of gravitational waves, where squeezing of a light was used to decrease the quantum projection noise. So on this, it turns out that the focus of our lectures will indeed be on this third kind of motivational pillar. And before I even get into that, I'll want to sort of make two quick remarks to frame the discussion a little bit. The first remark is an important one, which is that I'm mostly going to be focusing on the precision of measurements or the sensitivity. So oftentimes there's a distinction that one should carefully make between accuracy and precision. I like the classic example to distinguish the two of the bullseye. So, and you're shooting arrows at a bullseye, accuracy tells me how close I am to the bullseye, and precision tells me how clustered my arrows are. I'm going to make the assumption, as we often do, let's assume that we have designed a proper experiment. Let's assume we have designed a proper experiment to accurately measure a particular signal. The topic of accuracy and biases can be a lecture in its own right. And with that, we'll mostly be focused on precision. And in particular, the question of precision, I really want to frame as how many measurements does one need to perform in order to distinguish a small variation in a signal. Variation in a signal or a parameter that one is trying to sense. Parameter one is sensing. Okay. And I know that's not how, for those who haven't thought about sensing things or haven't thought about quantum sensing, that may not be the language that you're most used to thinking about stuff. But it is the proper language for estimation theory and the proper language for measurements. And in particular, this framing, I hope, will already give you a feeling that the thing that we're going to care about and the thing that will be very naturally appearing a ton throughout the lecture is the variance associated with the measurements and how the variance of those measurements scales with the number of measurements that I make. Okay? So we're going to be focused on questions of whether or not many particle entanglement can be used to enhance the precision of a measurement that we make. And in precision, I want us to think in the language of how many measurements does one need to perform in order to distinguish a small variation in a signal or a parameter. And the idea is that if your measurement has any dependence on the nature of the signal, and if you make enough measurements, you should be able to sharpen things and distinguish things that are kind of arbitrarily small, as long as you didn't do anything too crazy, right? This kind of just goes to the law of large numbers of the central limit theorem at some level. As you will see more clearly in the second and third lectures, one of the central goals for this series of winter school lectures is that I'm hoping to show you kind of a general principle, or to ask the question at least, is there a general principle for classifying slash experimentally making those types of quantum entangled states where the precision scaling can be better than classical. Okay, so that is an overarching goal that I will have for this series of lectures. Good. Before I even jump in, it's always good to start with a little bit of cold water. A bit of cold water to wake you up. To start, maybe I'll give a reference here. There's a couple good ones. Welga, PRL. That's just the year 1997. Zhou et al. Nature Communications, 2018. It turns out that this goal of trying to find quantum entangled states that exhibit a better scaling of the precision than would be allowed in our classical world in the presence of generic noise or decoherence, one cannot achieve, at least not asymptotically, one cannot achieve such an enhanced precision, such a quantum enhanced precision. Quantum enhanced precision. Okay? It's a really, really important thing to emphasize at the start, because I'm going to be telling you a lot of the things that are really, really interesting and cool about quantum sensing, give you a perspective here. But it is a truth that if you have generic noise and decoherence, one cannot achieve such a quantum enhanced precision scaling asymptotically. I don't mean to tell you that it means that quantum sensing is not interesting, but it does mean that you should really carefully note that the wins that you expect to take from quantum sensing are more nuanced. Twins must be more nuanced. And again, it's something that we will absolutely discuss in a little bit. All right. So before even entering the realm of quantum mechanics, let us start in the realm of classical mechanics, and let me teach you a little bit of the greatest hits, let's say, of classical estimation theory. Estimation theory. Okay. And in particular, let me state the problem very, very carefully. I always find that really understanding what exactly the statement of the problem is very important. And in particular, it's always helpful to understand the statement of the problem with an example. So the problem is that we are asked in general to construct an estimator, and you can find that this is really the kind of most general and kind of natural language for measuring a parameter or trying to estimate some parameter from a series of measurements. But it's going to sound a little bit of a formal tone. We're going to construct, the problem is going to be construct an estimator that takes in a particular sample set, a particular sample from some probability distribution of x given theta. All of this will be defined, and yields an estimate, theta twiddle, for our parameter of interest. Parameter of interest, theta. Okay. Okay, so it feels a little bit abstract, but I'm going to immediately give an example that will hopefully clarify things completely. The example is from one of my favorite papers. It's a super short read, so I really encourage you to all read it. It's by Francis Galton. It's a Nature paper from 1907, and the title of the paper is Vox Populi. And it concerns the estimate of the weight of a cow. You guys are too early morning for laughter. Okay. So we have the estimate, we have a cow, let's say, whose true weight is some random number, 1,100 pounds or so. So theta is its true value. And Galton was indeed interested in the variance, interested in sort of how best to make estimations of such a thing. And so you might say, okay, one strategy is simply to ask people to guess the weight of the cow. So you could say, so let's say person one guesses, I don't know, another random number. And so at that point, if you think about this from estimation theory, all I have, the only sample that I've drawn, I'm drawing a sample from a probability distribution. This probability distribution is the guesses that people would make of the weight of a cow. So individual measurements are given by x, given the true weight of the cow, which is given by theta, right? And for a single measurement, I might say, well, okay, the best I can do, assuming that I have, no reason to believe the person is particularly biased, the twiddle is simply going to be given as my estimated value. And for a single measurement or a single person, theta twiddle is simply equal to x1. No, nothing, I cannot do any better than that. Right? But if I have multiple individuals that give me more samples, x3 equals dot, 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 then of course, it's unsurprising to you that with measurements, I can make, let's put measurements in quotes here, I can make a better estimator, and someone should just yell it out just to make sure you're all awake. What is an obviously better estimator? Theta twiddle is equal to the average. Exactly. I heard it. Whoever yelled it, good. It doesn't mean exactly. Perfect. N of x. Okay. So this is like just setting up exactly what I mean when I say, we're constructing an estimator. An estimator is some function that takes in a sample from some probability distribution and yields an estimate for a parameter of interest. That probability distribution should somehow, in some sense, tell you about measurements and their dependencies on that particular parameter of interest. In this case, guesses from individuals of the weight of a cow, your parameter of interest. Okay. Perhaps the most central result, one of the most central results, a central result of classical estimation theory, estimation theory, is that the variance of any estimator is bounded by the so-called Kramer-Rao bound, independently independently discussed by Rao in 1945 and Kramer in 1946. And in particular, the Kramer-Rao bound says that, again, the variance, which I'll always use as delta theta squared, the variance of the estimator, which again is over all of your samples, the mean minus the estimate, is going to be greater than or equal to the bound, which I'll denote as delta theta Kramer-Rao squared. That's going to be equal to some C over N, where N is the number of measurements. Okay. Now it all feels a little bit abstract right now, and that's okay. It'll feel a little bit better. But I want to emphasize that you're very used to thinking about measurements and sensitivities in terms of, oh, I want to send something and I want to get a number out. I want to measure a particular number. But really, when we discuss parameter estimation, one of the most important intuitions to keep in mind and why everything I'm discussing here is really in terms of this notion of sampling from a distribution is that when you're trying to make estimates from a sample of a distribution, sampling from that distribution always leads to noise on the estimate. Always leads to noise. And so in some sense, the way you can think about where you're going to win ultimately, whether with the mean or something else, is that you want the variance to be as small as possible. This means that as you increase the number of measurements, you would like the scaling of the variance to go down as best as possible, because that means that you're really being able to sharpen your estimate. Again, we've assumed accuracy already. And by sharpening your estimate, it means that the noise is not so large that it would not allow you to distinguish between a very, very small change of the signal or a very small change in the parameter. That's why we use the language, and that's why when we think about sensing, it's always described in terms of variances. In some very, very intuitive sense, the content of the Kramer-Rao bound is really very, very simple and twofold. The first is kind of just central limit theorem. You have the very familiar scaling with n. In particular, the variance scales as 1 over n, which means the standard deviation scales as 1 over the square root of n. If you ask yourself, I'm trying to measure something, I do many measurements, and the mean peaks up, right? The mean peaks up because it grows as n, and the standard deviation only goes square root of n, so things peak up as the square root of n. Right? And the second kind of remarkable thing is that the coefficient, so that's not really all that surprising. The coefficient C is actually specified, and can be calculated. And we will certainly do some of those. We'll do an example calculation in a little bit. And in particular, 1 over this coefficient C is oftentimes known as the Fisher information. Fisher information, F of theta. And again, thinking back to this probability distribution that you are sampling from, right? Think about, it's really, you are making measurements and your measurements are being drawn from some underlying probability distribution. The measurements themselves must depend on theta in some way if you're going to have any information come out. And in the end, those will have some probability distribution. The Fisher information is defined as the sum over all of those possible outcomes, 1 over the probability distribution, and then the change in the probability distribution as one changes theta. I won't prove this, but I will say that it's kind of intuitive. The denominator tells you that the Fisher information gets smaller if the distribution is very, very broad. And the numerator tells you that you want to have something that exhibits a large change, a large variation of theta, so the slope should be kind of large. So both kind of reasonable. All right. So relatively intuitive result, but mainly I'm trying to get the right language for all of us to start discussing this question of quantum sensing. And I want to make sure, are there any questions at this stage? Okay, looks good. All right, so let's continue a little bit further. We'll still stay very classical, although I'll start calling this section quantum sensing. You'll find that we'll still be doing mostly classical calculations. Okay. And here, one of the things I want to note is that, in fact, the classical, what we just have above, the classical Kramer-Rao bound applies to unentangled quantum sensors, even if the sensors are small and governed by the rules of quantum mechanics, they can be totally in superposition. You can have a single spin degree of freedom or a qubit in a superposition of 0 plus 1. If you do not have entanglement between n sensors, then in fact the classical Kramer-Rao bound applies, and this, in the language of quantum sensing, oftentimes is what's referred to as the standard quantum limit. So I think sometimes people get confused. People hear the word standard quantum limit. They feel like there has to be something very quantum mechanical about it, that this means that, even if I have a quantum mechanical particle with superposition, that it's going to behave differently, or the rules for the parameter estimation are going to be different. But no, it really is the same as the classical Kramer-Rao bound. And as we did in the classical setting, let me start by now emphasizing already very early on that the nature of the problem and the workflow are just slightly different. And in particular, the nature of the problem and workflow in the context of quantum sensing is that there's going to be kind of an intrinsic need to sample from a distribution. Okay? And the sampling from the distribution is not necessarily just going to come from sampling from a classical setting, but it's going to be related to the fact that we need to perform quantum mechanical measurements in the first place. So let us restate the problem, sort of essentially the same. Say we are interested, I won't use quite as many words. So we're interested in calculating an estimate theta twiddle for a parameter theta, given now some quantum state row that has somehow encoded this theta. Okay. So again, you can feel that things are a little bit different because I've had to introduce this notion of a state already. And you'll see that difference a little bit more aptly when I very carefully write out the workflow that I envision. So the workflow that I have in mind, that we have in mind when we talk about quantum sensing, is maybe you could say a 4-step workflow. Step one, we will prepare a probe state row. I'm sort of using the Greek letter that one typically does for density matrices, which is trying to be general here. But actually, most of the lectures will focus on are where rho is really just a pure state. So it really just is just a projector onto a particular quantum pure state. But okay, so we imagine preparing some probe state. Then in step two, we somehow need to have the probe interact with the signal, and because we're in the rules of quantum mechanics, it should do so via some unitary evolution that is dependent on the signal. So for example, if this is a spin measuring a magnetic field, this can be Hamiltonian evolution under this magnetic field, in which case u of theta would equal e to the minus iht, and h, which encodes the strength of the field, or the parameter interested in theta, would live in the unitary u. Of course, once one interacts with the signal via the unitary, one has the state rho of theta, which is going to be u of theta rho original u dagger. Step three, we're going to have to pick, for example, some observable m and measure the probe state. Measure the probe state. We're going to pick some observable m and measure the probe state. What is this essentially doing? These measurements are exactly giving us a sample from some probability distribution P of m, the measurement result given theta. Again, it's a little bit abstract compared to the language, maybe just the intuition that you have for, oh, I'm just making a measurement on something. But it's this slight abstraction that allows us to analyze things much more carefully. You have your state. The unitary has been acted on it. The unitary encodes something about theta, and assuming that it does something to your state is now rho sub theta. When you pick an observable m and you make measurements, then these measurements are exactly a sample from the probability distribution of P of m given theta. So you're saying in some sense, there's kind of a, measurement in a quantum measurement here, measurement is doing the sampling, is one facet of the sampling. And then step four, I need still, of course, as with all cases, but the classical or the quantum setting, I need to do some type of post-processing. This could be a method of moments. This could be maximum likelihood estimates. I need some estimator to ultimately figure out what I think theta twiddle is. Okay, good. I hope everything has been very, very clear thus far. Is it very clear what the setting is? I can't see you all that well, but I'm assuming that no sound is good. Okay, so now, as I always liked when I was a student, I'd like to see an example in action. Okay, so the goal of this example is to really show us that we should get back the classical Kramer-Rao bound. We're going to do this for instead of a single quantum spin degree of freedom or unentangled quantum degrees of freedom. And so we should ultimately get back the classical Kramer-Rao bound, which in the context of quantum sensing is often called the standard quantum limit. And the example that we're going to focus on and kind of do out in gory detail, because I think it's really helpful to see it done out in gory detail. I wish when I learned quantum sensing, someone had done this for me. We're going to look at an example which a single quantum spin degree of freedom, used to estimate what it does best, the strength of a magnetic field. And we're going to do so via the standard tool of Ramsey spectroscopy. So I will, and always in these lectures, one only has a given amount of time, so I'll almost have to assume some background knowledge in various things. In this case, I'll assume a little bit of a knowledge on Ramsey spectroscopy and the Bloch sphere, how to think about this. If there are questions, though, don't just feel you need to sit through it. Just ask questions. So the signal we're trying to sense is some magnetic field strength B, and it's coupled to, for example, let's say it's along the z-axis, so it's coupled to the sigma z operator, the spin operator of my spin 1/2 object. Let's be very, very slow and methodical here. So we'll write out this sort of Ramsey sequence. So let's see. So Ramsey sequence, you start with a spin, for example, pointed along either up or down, and you apply something colloquially known as a pi/2 pulse. Pi/2 pulse, I'll draw what it does on the Bloch sphere for those of you that don't know. Then step 2, okay, I'll try to draw this kind of long. These are not a little bit related to this. And then we'll have a final thing over here, and then we'll have a measurement over here. And the measurement is going to be, and I'll try to draw things. So I think all of you are familiar with the Bloch sphere. It's a nice, very, very helpful representation. Maybe I'll draw a little bigger. Very, very helpful representation of a qubit or a spin 1/2 degree of freedom. So if one starts, for example, with a spin aligned along the spin up or spin down, the z direction, then by pi/2 pulse, all I mean by that is I'm just putting the spin aligned along the equator. For example, let's say it's aligned along an x-axis, but I'll say that the x-axis is such that the quantum state is down plus up. Step 2, I'm going to evolve under my unitary. This is going to be u of theta. I need to acquire the signal. This will be e to the minus I h prime t for some period of time. Let me just see how adept I can be at this. So step 2, let's say that my spin was originally in this direction. And now let's say if the field is along the z direction, you know intuitively what it's going to do. It's going to Larmor precess. And the Larmor precession angle is going to be given by theta equals b naught times time. If you're very, very careful about your timing, then once you can estimate theta, which is the parameter we're interested in, then you can immediately back out the strength of the field. Okay. And so after step 2 of our acquire signal, unsurprisingly, you now have each of the spin up and spin down simply pick up a phase according to the strength of the magnetic field. So if we split the phase equally, it's e to the I theta over 2, let's say up, plus e to the minus I theta over 2 down. Okay, super easy. Let's try it one more time. So this final pi/2 pulse, I'm not even going to necessarily include it. You can think about it as part of the measurement step, but one way or the other, I think that's okay. I'll write step 3 up above over here. Whether you think about it as part of the measurement step or as part of the signal. Oh no, sorry, I just shut off my iPad screen for a second. Apologies for that. Do I need to share again? I think so. Let me try. Hold on one second, guys. All right. Do you see my screen again? No? Uh-oh. Okay, hold on. Hold on. Hold on. Okay, let me see. Hold on. Let me try to go back and try it one more time. Share screen, start broadcast. Okay. Let's see. But I think now, hold on. Somehow Zoom has dropped off. Give me 1 second. Let me see if I can. I don't know if my iPad's on Zoom anymore. Hold on 1 second, guys. Give me, oh, I'm sorry. So let me try to go to this. Oh, it still says I'm here. It says nobody else is here. Let me see. All right. Apologies for that. Always have some small technical issues. I'm not sure why we are having issues with this. All right, give me 1 second, guys. Somehow Zoom is unhappy, which as an app, it tends to do. But let me just see, is it an internet problem or give me 1 second. Okay, I think we'll be good now. At least fantastic.
Recording in progress.
All right, I think I'm back. Let me share screen. Okay. All right. Are we back in business? I think so. Let's see. All right. Let's take a look. All right. Can people see my screen again?
Yes.
Fantastic. Sorry about that technical complication, as they say. Okay, so good. Okay, so we were on step 3. We were just about to perform our second pi over 2 pulse, which of course all of you can already guess, even if you haven't seen this before. What the second pi over 2 pulse does is it simply changes the phase information kind of in the equatorial plane into information in the latitudes, so into the z-axis. So theta is now encoded over here. And in particular, your quantum state is now given by psi of theta is equal to cosine of theta over 2 up plus I sine of theta over 2 spin down. Okay. So this is a very, very standard Ramsey spectroscopy sequence. Many of you have done this in your experiments for sure. At the same time, it is also follows very, very standardly kind of what I've mentioned is the step-by-step process for the workflow of thinking about a quantum sensor. And most of you would say, okay, if I needed to estimate this, I would just do it. I would just sort of do this type of a thing and just back out a value and tell you the strength of the magnetic field. But of course, what we're interested in is how precisely we can make such measurements, and thus we ultimately care about the variances associated with making an estimate on theta. Of course, in this case, the most natural thing to do is to make a measurement, for example, of sigma c. So now let's analyze this very, very familiar thing in the language of what we've been talking about, which is the language of thinking about these probability distributions, these variances. What exactly does that mean? I'm going to ask yourself, what does P of m theta look like for this type of a scenario? Okay, we'll try to keep the picture up here. Well, let's ask ourselves that. What does P of m theta, what does that probability distribution look like? So this theta is, give some markers here. Pi, 1, 1/2, and 0. Okay, maybe let me ask a question. Okay, so let me just ask, someone call out, please, please humor me. Uh, what do you think the probability distribution looks like for P of m theta, let's say for either m being up or m being down? You pick which one you want. Answer's kind of already there. Some brave soul has to call out, or someone has to pick someone who's holding their hand up because I can't see. Say it one more time.
It's a squared sinusoid.
Sorry, one more time. Somebody closer. Say what was just said.
I think he says square sinusoidal.
Square says there we go. Exactly. So, for example, for if m is equal to if m is up, if the measurement is up, then it's got to be cosine squared. Let's see what that looks like. It'll probably look something like this. Goes to here. And if for the m equals down one, it's got to be the exact opposite. So it's got to be not drawn very well. Sorry, not drawn super well to scale. That's pretty bad. Let me try to redraw that a little bit. Okay, good. Square sinus, right? Exactly. So we'll just dot right here. So indeed, this is we're defining a framework, and I'm trying to give an example of using this framework, although you don't yet know how powerful the framework is. So for m equals up, that's clearly for if you measure up, the probability distribution is going to be cosine squared of theta. And here, if you measure down, it's going to be the opposite. And it makes sense. I hope I've gotten it right. If theta is equal to 0, then this is at the North Pole. So then I should have m being up being 1 and m being down being 0. Good. Good. But what you can kind of tell from this is the following. You can immediately see that a single measurement of sigma z equals up, aka plus 1/2, doesn't really tell you all that much about the parameter you're trying to estimate theta, right? If you measure up, there are many different probabilities. There are many different theta that all have some non-zero piece of the probability distribution, right? Again, I really do hope that what I'm saying, this should feel, I hope, very, very natural to you. You're analyzing a problem that you hopefully have seen before, but in a language that I'm forcing you to think about, which will be in the language of Fisher informations and Kramer-Rao bounds, but it will be the very powerful way to analyze things. Okay? But clearly, you can see this is not surprising to you. If you're doing experiments, you know that you know how to measure a bunch of times to figure out expectation values in the first place. But from this probability distribution, we can see that a single measurement of sigma z equals up doesn't really tell you all that much about theta. Okay. And now the question I want to ask now, as we continue to analyze in this way, is how does this change? How does this change for n spins? Okay. And I want to call out for you, just because it's abusive notation by choice. This is an abusive notation. In principle, there is a number of spins, a number of particles that make up my sensor, and there's also the number of measurements that I do. They should be different variables. For this purpose, because I'm going to think about uncorrelated sensors, it sort of doesn't really matter all that much if I take them, I can sort of exchange one for the other. So this will be an abusive notation, but sort of to prove a point for now. And the point here is that this is for, we have uncorrelated sensors. Okay, but in principle, once one, for example, starts discussing entanglement, those two parameters should absolutely be distinguished. Again, how does this change for n? Well, your purely classical intuition, I mean, again, we're talking about a Ramsey experiment, which feels like, when people talk about quantum mechanics, they say, oh, Ramsey spectroscopy, that's like a standard quantum experiment. But of course, from the perspective of estimation theory, it's all governed by the rules of classical estimation theory. And our purely classical intuition says that eventually things, at least in terms of how sharp things go with standard deviations, should go as 1 over the square root of n. Okay. And maybe let's try to sort of, state 2 even more specific limits of intuitions that one has. If one does this for n spins, and one thinks about the measurement that I'm doing at the end as sigma z total, that's the sum over all of the sigma z's of the individual spins, then clearly there are 2 things that are obvious. If one gets a big value of sigma z total, then the distribution should be more sharply peaked at theta equals 0 or pi. And again, I'll try to illustrate this with pictures in just a little bit. But clearly, if one gets a big value of sigma z, then one expects, from the perspective of the probability distribution, the distribution should be sharply peaked at theta equals 0 pi, just from knowledge of the physics. The second is that if one gets a small value of sigma z tot, somewhere, for example, around 0, then you expect that the distribution should be peaked around theta equals pi over 2. Okay? So we can literally compute, this is a very easy combinatorics question. You can literally easily compute what P of sigma z tot given theta is. And I'll just write the formula down from you. It's n choose n over 2 plus sigma z total, the square root of that. Let me just make this a little bit more legible. I apologize. Times, and you can imagine what this has to be, cosine of theta over 2 to the n over 2 minus sigma z total multiplied by sine of theta over 2, this is the opposite one, n over 2 plus sigma z total, and all of this squared. Okay, again, it's just combinatorics. You're measuring n spins, just combinatorics. So what does this look like? What does this look like? Well, let's take an example. I'm going to draw it for you, but I planned this night. You can do this very, very quickly in Python. Again, I really want us to sort of start thinking about things in this language, is why I'm drawing all these plots, even though, again, you're thinking about something that you should be pretty, well, many of you, I suspect, are reasonably familiar with this Ramsey spectroscopy. Same thing, thinking about what exactly does the probability distribution of P of sigma z total equal. So assuming I have spin 1/2 particles, the maximum I could get for sigma z total is 10. And if I get sigma z equals 10, then you know that the probability distribution should be very, very sharply peaked around 0. And similarly, if I get minus 10, I should imagine that the probability distribution is very, very sharply peaked here. And if I get an intermediate value, you should imagine that, of course, on either side, I'll start having probability distributions. For example, let's say this is sigma z total equals, I don't know, 7, or sigma z total equal -7. So this is -10 to -7. And then, of course, sigma z total equals 0 will be somewhere over here. Sigma z total equals 0. This is trying to quantify in some very, very precise way what the information content is of making a particular measurement result. It is asking what is the underlying probability distribution that that measurement result came from, given changes in the parameter that you are trying to sense. Is this intuitively clear to everyone? Good. I think that's a yes. And just because we've really been defining things in terms of Fisherman, we should get back, right? In the end, we should get back to standard deviations. Central limit theorem tells you that at the end, you should get back to a scaling that looks like 1 over square root of n. You're just doing Ramsey spectroscopy on a single spin, trying to estimate a particular field or a particular angle theta. So you should get back to that, but let's see how we get back to that using this slightly more complicated but powerful machinery. And in particular, one can immediately ask, now that we've literally written down what P of sigma z total theta is, what the probability distribution is, we can ask, what is the Fisher information? What is the Fisher information associated with this particular measurement for the parameter theta? Well, f of theta, of course, as I said, is going to be a sum over all of the possible values of sigma z total from minus n over 2 to n over 2, 1 over the probability distribution, sigma z total theta, and then derivatives of the probability distribution, total theta squared. And you will find, if you do this calculation, that the Fisher information is given by exactly n. It's not so much the n scaling I want to focus on for just a second. It's rather that this is completely independent of theta. Independent of theta. You might have thought, just thinking about cosines and sines, that from a slope perspective, that certain angles you should be more sensitive to. The derivative of a cosine certainly has some, certainly has a larger slope at the midpoint than at the peaks and the troughs. Can someone give some physical intuition for maybe, it doesn't have to be precise, for maybe why this is independent of theta, which at its outset looks like a pretty surprising result to me? Anyone give me a feeling for why it's independent of theta? Why is the Fisher information independent of theta? No takers. Okay. So it turns out the reason for this is something that we'll get into a little bit more, but the reason is because you have both signal and noise. And it turns out that the signal is indeed enhanced, but it turns out the noise, the sort of intrinsic variance associated with measurements at different angles, is also different. And those two things cancel exactly perfectly so that it's completely independent of theta in this case. Okay. And what I mean by noise will be a little bit more clear in the next series of lectures. And I want to emphasize that already by computing the Fisher information, I would say that you can kind of gain what I would call sort of dual perspective, a dual perspective on the scaling of such an n spin Ramsey sensing experiment. Okay. Okay. Perspective one is just the analysis that we did above, the analysis that we did above. In particular, we thought of everything in terms of literally one big spin. Well, obviously we did because we were talking about measuring things like the collective spin operator. But we really only measured the collective spin operator once. So in that sense, capital N, in the first way I define things, the number of measurements is just one. And so if you remember the Kramer-Rao bound, we know that the Kramer-Rao bound is going to be equal to C over N, which is C over 1, because there's only one measurement. And C itself is 1 over the Fisher information, and the Fisher information we just found out was N, so this looks like 1 over N. And this means that the standard deviation of my estimator is 1 over the square root of N. And that makes sense. If you're doing a Ramsey experiment trying to estimate a magnetic field, and you do so with n spins, you expect that the standard deviation of that estimate goes down as 1 over the square root of n. Central limit theorem. A complementary analysis is, let's imagine thinking about this as a single spin 1/2, but that we instead measured n times. Okay. So now the observable m is just sigma z. Unsurprisingly, the Fisher information in this case, again, you can figure out what this is by plugging in for n equals 1. The Fisher information is 1 because there's no scaling with n. And you find exactly the same scaling. It equals c over n, where c is equal to 1, and the n all comes from the number of times that you do that measurement. Again, the standard deviation goes as 1. So this indeed gives you a feeling for, in the unentangled case or the uncorrelated case, whether you're quantum mechanical or classical, you can kind of trade off, in this case, between the number of measurements you do and the number of particles you're using, because each of those is just an independent measurement. And that's indeed why, ultimately, when we think about things, we'll express sensitivities and precisions oftentimes in terms of 1 over the square root of the time used to acquire that signal. And oftentimes in your mind, that time acquired a signal, you could use more sensors independently to acquire a signal within the same time. You could exchange t for 1 over square root of n. Good. Okay, but let's continue for a second. So thus far, we've now sort of introduced kind of what I think about as a classical question. Then we've introduced a question that's more the workflow of quantum mechanics. But both of those have been analyzed and correctly should be analyzed in the context of our expectation that they should be bounded, their variances of the best estimator you can do, by the classical Kramer-Rao bound. And so here, I'd like to start by quickly now introducing, just for a little bit, the quantum Kramer-Rao bound. So as I have emphasized multiple times, the Kramer-Rao bound depends on the particular set of measurements that one has chosen to do. And maybe one spiritual difference for the quantum Kramer-Rao bound is that it kind of is defined a little bit differently, which is it says, considering all possible measurements, what is the optimal Fisher information given a particular quantum state rho. So the Fisher information is defined for, in this case, a quantum state rho and a particular measurement observable. And the quantum Kramer-Rao bound considers all possible measurements. So clearly, you immediately know that the classical, it's got to be better than the classical Kramer-Rao bound, which means that delta theta Kramer-Rao must be strictly greater than or equal to delta theta quantum Kramer-Rao. And again, here I'm going to try to probably, still not immediately now, but I'll ultimately start making distinctions, which is that here n is going to be the number of measurements. And then over here, instead of just having a c, a sort of some coefficient that's related to the Fisher information, I'll write it down explicitly. The quantum Kramer-Rao bound is given by optimizing over possible measurements m. The Fisher information, I'll sub it q, because oftentimes this is now called the quantum Fisher information, where it's the Fisher information taking in a particular state rho of theta and doing the measurement n. So spiritually, it's exactly the same. The classical Kramer-Rao bound was C over n. C was related to 1 over the Fisher information. The quantum Kramer-Rao bound is 1 over n. C is related to 1 over the Fisher information, but now the Fisher information is optimized over all possible measurements. Okay? It's just a definitional difference, really. It turns out perhaps the most useful formula, the most useful version of the quantum Fisher information is for pure states, for pure quantum states, which is, again, what most of these series of lectures is going to be about. You'll find that this quantum Fisher information for my state rho theta and my measurement m hat is given by 4 times the variance of the measurement m in the state rho theta. So again, just write that out in English, for example. This is the variance of the observable m in the quantum state rho theta. So as you have hopefully had it beaten into you now at this early hour in the morning, in the end, when we talk about sensitivities, things like that, it's all related to variances. So it's another place where variance appearing. The variance of m in the state. And I'd like to consider just before, actually, Hossein, I'm going to take, I don't know what this schedule is exactly. Is it okay if I take maybe just another 5 minutes or so?
Yeah, sure.
I just want to make sure. Yeah, sorry, because I think, anyways, there was a little hiccup with my screen sharing, but just to get to a nice stopping point. Thank you so much. Okay, so this,
You can hear me now, right?
yeah, I can hear you now.
Oh, okay. So, yeah, I think we should sort of aim toward half past hour. I think should be just fine.
Okay, fantastic. Yeah, no, I hopefully won't go that long just to give some questions, but yeah, that'd be great. So let's really try to get a little bit of intuition for ourselves by considering 2 helpful limits. In particular, case 1. what does it mean if the variance delta m squared, uh, delta m squared is equal to 0? This, of course, means that the quantum Fisher information is also, by definition, what I wrote up there is also equal to 0. When would it happen that what does it mean? What does it physically mean if the variance of the observable is 0 in this particular state, rho theta? It's not a trick question. Somebody just call it out. What does it physically mean?
This was deterministic.
Yes, yeah, that's like a different English word for what I said. It says, yeah, but what about yes, that it's deterministic. Yes, that's right. I agree. But what more can one say about uh, yes, perfect. I don't know who said it, but I heard, I didn't even hear many words. I just heard one word, but the word was correct. It was eigenstate, exactly. This implies, of course, that rho theta is actually an eigenstate, of the operator, the observable M. And thus, it means that evolution under rotations that encode theta commute with M, and thus you have no sensitivity to them. That's the easy case. Let's consider the slightly more hard case, which is how does one get the maximum quantum Fisher information? How does one get the maximum quantum Fisher information in this type of a setting? Well, I'll walk us through this a little bit more. It's always helpful to think about, so we're doing measurements, let's always think about the eigenbasis. Let's think about the eigenbasis of M. In particular, let's imagine that the eigenbases are given by little mi kets, which have little mi eigenvalues. You immediately know, by definition, the variance is bounded from above by the maximum eigenvalue minus the minimum eigenvalue. You immediately know that. You immediately know that the variance is bounded from above by the maximum eigenvalue minus the minimum eigenvalue squared, because it's a variance. Again, I guess it goes without saying, but we are always trying to, okay, maybe I'll say it anyways. In the end, we're trying to push down the variance of the estimator so that we can we can discern small changes in the parameter theta with the smallest number of measurements, spins, etc. Because the Fisher information lives in the denominator, you always want a large Fisher information. Okay. The Fisher information over here basically depends on the variance of M in the state rho. And that means you want a large variance here. That's different than the variance that you want for delta theta squared. Okay. So there's two variances that enter. They enter everywhere. Sensitivities are always about variances, but they enter differently in this context. Okay. So the variance for delta m squared is bounded from above by the maximum minus the minimum eigenvalue squared. And we can ask ourselves, is there any pure quantum state? Sorry, the writing's bad. Is there, oh no, what happened? Annoying. Let me just see what happened. think you guys somehow Zoom gave me a little issue, but I don't know what it is, but I'm still here. It literally just says the screen sharing stopped unexpectedly. That was the notification I got. So let me try to share it again. It looks good to me. Okay, good. All right. Are we back? Clear? Is there any pure quantum state that can saturate this? All right. Somebody call out. Is there any pure quantum state that can saturate this bound? Can you think of a pure quantum state that would be able to saturate this bound? Again, maximum variance means maximum Fisher information, means in the denominator, minimum variance of our Kramer-Rao, minimum variance of the estimator. Just call it out.
An equal superposition of the max and the min.
Perfect. Whoever said that, fantastic. Exactly. So the answer is yes, exactly. It is the cat state. So again, sorry, who was that?
Francisco.
Oh, I see, Francisco. That's not so fair. All right. So indeed, well, thank you, Dr. Machado, for your insights. So the cat state, yes, exactly. But it's the cat statement. So again, a lot of these words for quantum sets you've heard before, the GHZ state, Ramsey spectrum, you heard all these concepts before, but I'm trying to formalize it in the right framework, which is the framework of Fisher informations and Kramer-Rao bounds. So the cat state, which is psi cat equals 1 over square root of 2, let's say, as Francisco said, of the eigenstates M max and M min, exactly satisfies that. And so let's just go back very, very quickly. Going back very quickly to our example of n spins and thinking about sigma z total as the observable. You know that m max is then going to be equal to n over 2. You know that m min is then going to be equal to negative n over 2. And this, of course, means that 4 times delta m squared is going to be less than n squared. And this means that, contrary to what we found in the classical case, thus, okay, it's not that surprising because now you know the answer, but let's write it anyway. Surprisingly, with a cat state version, the cat state version of one big spin, even with a single measurement, n equals 1, you find that delta theta squared, how small you can make the variance of the estimator, goes as c over 1, but c now goes as 1 over n squared. And this means the standard deviation of your estimator can improve as 1 over n, the number of entangled spins in your systems. This is the so-called Heisenberg limit. Heisenberg limit of sensing. Okay. So this is really the essence, what we've said here. This above, the above, is really the essence of the quantum Kramer-Rao bound. Kramer-Rao bound, which is that the variance of an estimator, again, we'd write down the exact same formula, theta minus theta twiddle squared, is greater than the variance, the quantum Kramer-Rao bound, QCR squared, which is equal to sum C prime over n squared. Whereas in the classical case, it was 1 over n. In the quantum case, I'm writing it as 1 over n squared. Okay, I have a little bit more I wanted to say, but I think this is a pretty optimal time to stop. All right, thanks for listening, everyone. Feel free to ask questions. I'm happy to take questions.
Very much, Mark.
Questions? You can't raise your hand, you have to speak up.
You also feel free to email me questions afterwards. That's also no problem. I'm happy to respond to email as well.
Thanks very much.
No? All right, maybe it's too early in the morning.
No worries. Or it was so clear. That's what I'd like.
Absolutely. That part is definitely the case. Yes.
Good. Okay, fantastic.